In 1969, 12 humans walked on the moon using controlled explosions strapped to their feet. In 2024, we are still using controlled explosions. At the speed of our fastest spacecraft ever launched, reaching the nearest star system outside our own would take 73,000 years. That is not exploration. That is a prison sentence written in physics. Here is why rockets are broken as a tool for deep space. They work on a simple principle. Burn fuel, generate exhaust, use the reaction to move. Newton's third law, elegant, proven. The problem is what mathematician Konstantin Tsiolkovsky calculated in 1903. The faster you need to go, the more fuel you carry. The more fuel you carry, the heavier you become. The heavier you are, the more fuel you need just to move that extra fuel. It becomes a cycle that eats itself. To send 1 kilogram of cargo to Mars and back, you need hundreds of kilograms of propellant. Go further, and the numbers become impossible. This is the wall humanity has been staring at since we first looked up at the night sky and asked how to get there. The answer is not one technology. It is 7, and the scientists working on them are not writers. They are physicists and engineers, and some of them believe they are close. Ion thrusters already exist and are already flying. Instead of burning fuel explosively, they electrically accelerate charged atoms, ions, out of the exhaust nozzle. The thrust is so gentle you could barely feel it against your palm. But in the friction-free vacuum of space, that gentle push compounds over months and years of continuous operation. The efficiency metric is called specific impulse. Chemical rockets score around 450 seconds. Ion thrusters score between 1,500 and 10,000. 20 times more fuel efficient. Dawn, NASA's asteroid belt mission, used ion propulsion to orbit 2 separate rocky bodies, something no chemical rocket could have attempted. Next-generation nuclear-powered ion drives could cut a crude Mars trip from 9 months to roughly 90 days. The limitation: they accelerate slowly. You cannot use them to launch from a planet. For that, you need something else entirely. The most expensive part of any space mission is the first 200 kilometers off Earth. The entire rocket problem largely exists because of those 200 kilometers. The space elevator bypasses them entirely. A cable anchored at the equator, extending 36,000 kilometers to a counterweight in geostationary orbit, stays taut through centrifugal force. Attach an electric climber, essentially a car on a rail, and ride it to orbit. No fuel, no explosion, just electricity and patience. Current launch costs sit between $1,500 and tens of thousands of dollars per kilogram. A space elevator could bring that to $100 or less, a 90% reduction. The obstacle is material science. The cable must be stronger than steel, lighter than almost anything we have, and 36,000 kilometers long. The only candidate is carbon nanotubes, which exist, but currently only in strands millimeters long. The day someone manufactures them at scale is the day this project moves from theory to construction. Japan's JAXA conducted a small proof-of-concept test in 2018, a miniature climber between 2 satellites. It barely scratched the surface. The idea is alive. In the 1960s, the United States built and tested a functional nuclear rocket. It worked. It outperformed chemical rockets by a significant margin. In 1972, it was canceled. Nuclear thermal rockets heat liquid hydrogen using a reactor instead of combustion. Because hydrogen is the lightest element, it exits the nozzle faster than any combustion product, delivering dramatically better efficiency. A nuclear thermal rocket could cut a Mars journey in half. A more advanced concept, nuclear pulse propulsion, using sequential controlled detonations, could make the trip in under 2 months. In 2023, DARPA and NASA announced an active program called DRACO, targeting an in-space nuclear thermal propulsion test by 2027. This is a funded government program, not theory, not a proposal, a test flight. The concerns are legitimate: radioactive material, launch accident risk, political complexity. Advocates argue the reactor stays cold during launch and is only activated in space, dropping the risk profile significantly. The engineering is largely solved. The debate is ongoing. Light has no mass, but it carries momentum. When a photon strikes a reflective surface, it imparts a tiny push. Individually, nothing. Collectively, across millions of square kilometers of sail in frictionless space, it moves a spacecraft. Japan proved it in 2010 with Icaros. The Planetary Society proved it again in 2019 with LightSail 2, which used solar pressure alone to raise its own orbit. No propellant. The limitation: Sunlight weakens with distance. Past Jupiter, solar sails lose power rapidly. The electric sail proposed by Finnish scientist Pekka Janhunen solves this. Instead of catching photons, e-sails catch the solar wind, charged particles streaming from the sun at up to 800 kilometers per second, using long electrically charged wires. Solar wind extends far beyond Pluto into interstellar space. No fuel, no reactor. Preliminary calculations suggest e-sail spacecraft could reach 30 kilometers per second, fast enough to exit the solar system in roughly 20 years. Voyager 1, nuclear-powered, took over 35. A conductive tether moving through a planetary magnetic field generates electromagnetic induction. Same principle as an electric motor, but running in reverse. Run current one direction, boost your orbit. Run it the other, slow down and deorbit. No propellant required. NASA tested this in 1996 from the Space Shuttle. A tether nearly 20 kilometers long that generated far more electricity than anticipated before snapping from electrical overload. A failure in execution. A proof of concept. Momentum exchange tethers could act as a slingshot in orbit, transferring energy to a spacecraft and sending it toward the Moon or Mars without burning a drop of fuel. Electrodynamic tethers could deorbit dead satellites, helping solve the growing space debris crisis. Low cost, passive, underappreciated, and almost entirely underfunded. In 1994, physicist Miguel Alcubierre found something inside Einstein's general relativity, equations that no one had looked for. A mathematical description of a spacecraft moving faster than light, not by breaking the speed of light locally, but by warping the space around it. Contract space in front, expand it behind. The ship doesn't move through space. Space moves around the ship. The problems are profound. It requires exotic matter, matter with negative energy density, which may not exist. Early energy estimates were equivalent to the mass of Jupiter, converted entirely to energy. In 2012, NASA physicist Harold White proposed geometric modifications that dramatically reduced the requirement. Still enormous, but no longer Jupiter. In 2021, researchers proposed positive energy warp solutions requiring no exotic matter. They cannot exceed light speed, but they could approach it, potentially placing Alpha Centauri within a 5-year journey. The warp drive is the longest shot on this list. It is also the most consequential if it ever works. In 2016, Stephen Hawking stood on a stage and announced Breakthrough Starshot, planned to fire a 1.0 gigawatt ground-based laser array at a gram-scale spacecraft attached to a microsail. In 10 minutes of sustained laser fire, that starship reaches 20% of the speed of light. It arrives at Alpha Centauri in approximately 20 years. Voyager 1 would need 73,000. The engineering challenges are real. Laser focusing through atmosphere, thermal survivability, communication across 4 light years with no way to slow down upon arrival. But the underlying physics is not theoretical. It is known, confirmed, tested physics. Smaller scale applications are already being researched. Space-based laser platforms pushing cargo to Mars in weeks using continuous beaming with no fuel aboard the spacecraft at all. In 1903, the same year, the Wright brothers flew 37 meters at Kitty Hawk. Experts debated whether powered flight could ever be practicable. 66 years later, humans walked on the Moon. These 7 technologies are not equal. Some are nearly ready, some may never be built. But ion propulsion is already flying. Nuclear propulsion is being tested by 2027. Solar sails have been proven in orbit. Lasers are being pointed at the sky. The picture that emerges is a cascade, each technology extending the reach of the last, each one pushing the boundary of where a human being can go and return from alive. We are a species that evolved to cross savannas, now building machines to ride starlight to other suns. And we are just getting started. Of everything in this video, which technology do you believe humanity actually builds first? The space elevator? The nuclear rocket? The laser-propelled starship? Drop it in the comments. I read everyone, and these debates are worth having. If this made the universe feel bigger and the future feel closer, subscribe. We cover the science that reshapes how you see everything. See you there.